Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Kiyoshi Masui, who is Assistant Professor of Physics at Massachusetts Institute of Technology. He works to understand fundamental physics and the evolution of the universe through observations of the large-scale structure, the distribution of matter on scales much larger than galaxies. Welcome, Kiyoshi.
Thank you.
Yeah, thanks for doing this. So I have a few papers here by the CHIME FRB collaboration, and we'll talk about CHIME a little bit. But the first one, observations of fast radio bursts at frequencies down to 400 megahertz. The paper talks about fast radio bursts are highly dispersed millisecond duration radio flashes, probably arriving from far outside the Milky Way, our own galaxy. And this phenomenon was discovered at radio frequencies near 1.4 gigahertz, and so far has been observed in one case as high as 8 gigahertz, but not at below 700 megahertz, in spite of substantial surges at low frequencies. So before we get into the details of this, Kiyoshi, fast radio bursts, we have radiation at the radio part of the electromagnetic spectrum all around the universe. What makes these bursts special? What are the characteristics that make them fast radio?
Fast radio bursts, or we just say FRBs mostly. And so, they're exactly what as they're described. So they're radio bursts, and the fast part just means that they're very short duration, right? Typically milliseconds long. So it's kind of like a camera flash, really, except for in the radio part of the M spectrum.
Okay.
And the thing that makes that kind of special is that a long-standing, a classical argument in astronomy is that you can't have large objects making fast signals. Okay, and the reason for that is geometric, right? So, for instance, our sun. What is the shortest signal our shortest burst our sun could conceivably make? And the answer to that is that the sun can't make a burst that's any object the size of the sun can't make any signal that's shorter than, say, several seconds long.
Yeah.
And the reason is it's just because it's geometrically large, and the time, the sun is several light seconds across. So that if the sun made, if it tried to make a very short burst, it would still look to be like a long burst to us, seconds long, just because, it takes time for the light to reach us from one side of the sun to the other, right? And that geometrically smears out these flashes. And so the thing that makes these special is they're milliseconds long. It means they're coming from objects that are only like tens or maybe hundreds of kilometers across, which is, from an astrophysical point of view, just very, very tiny.
Right. Yeah. And so two characteristics, it sounds to me, Kiyoshi. One is the frequency, and the other is the duration. And so duration, as you say, is going to be very, very short, millisecond duration, like you said, like a flash of a camera. And the other is the frequency at which it arrives. And there is a whole spectrum of frequencies there, right? And so this particular paper is talking about FRBs at sort of lower frequency in the range of 400 to 700 megahertz.
Yeah, that's right. So this had never been observed before. So we built this instrument, CHIME. It's a radio telescope, which I'll talk about a little bit more later, hopefully.
Yeah.
And it's built to observe a certain frequency range, which is from 400 megahertz to 800 megahertz, and that's just like any telescope, right? You have to build it for a specific part of the electromagnetic spectrum, and that's the choice we made for this particular telescope. And it wasn't clear that these fast radio bursts occurred at these low frequencies. That one of the most common frequencies to observe in radio astronomy is at 1 to 2 gigahertz. The reason is that there are protected bands there. There are places where cell phone carriers and stuff just aren't allowed to transmit at those frequencies because they're protected for radio astronomy, and that eliminates a lot of the interference. And so that's the most popular place to do radio astronomy, and that's where all these FRBs had been observed before. But we took a risk and built this telescope that observes at different frequencies because of one of the science goals of CHIME, not the fast radio burst one, but another one, required those frequencies, and it wasn't clear we were going to see fast radio bursts there. So this first paper was the first fast radio burst that this instrument had ever seen. To a certain extent, it was just a big relief that we built this big telescope and were able to see things that wasn't guaranteed beforehand.
So the FRBs themselves are sort of a recent phenomenon, right? So when did we first observe an FRB?
So the first FRB was discovered in 2006, 2007, 2008, depending on exactly how you count when it was discovered or when the paper came out, whatever. But that was actually in data that was collected in, I think, 2001. So that the data was collected at the Parkes Telescope in Australia. And it sat on disk. It was used for other things, but no one had looked for these very short radio flashes in that data. And then someone, Duncan Lorimer, bravely did a search, a very speculative search. He didn't think he was going to find anything. He just said, what if we look for flashes in this data? There was a flash in that data, and that was this sort of very iconic result in radio astronomy. That was the first fast radio burst. And then for 5 years, there was a lot of speculation in the field of whether this was whether that was a real signal or if it was just some glitch in the telescope. No one was absolutely sure that this was a real thing. But it wasn't until I think 2013 when we went from one of these known flashes to a handful of these known flashes. And, another survey using the same telescope discovered 4 of them. That it was that people started to become convinced that this was a real astrophysical phenomenon.
Yeah. So it is a little bit intuitive, as you mentioned, and so we found it sort of accidentally in 2007, 2008 timeframe. Since then, we had I believe we had 50 or so FRBs observed, and the counterintuitive part of this is it's the duration, right? It's a flash, and as you say, large objects cannot make things that shorter duration. So this has to be something
that is very dense and very powerful, like a neutron star or something like that? Is that the idea right now?
That's exactly the idea. So and we'll narrow down on that a little bit, and some of the other papers that uh, we might get to talk about, right?
Yeah.
But since day one, people thought, well, neutron stars. This has to be a neutron star because you need energy to make this very powerful flash, right? So we see these things coming from halfway across the universe, very, very far away. And so since we can see them coming from places that are so far away, they have to be very powerful intrinsically.
Mm.
Um, but they're coming from very tiny objects, 10 kilometers across or something. And there's really only one astrophysical candidate that works, and that's a neutron star. No one knows how the neutron stars are doing this,
Mm.
but people are pretty sure that neutron stars have to be doing this because you need something that has the energy and is physically small in order to do this.
Yeah. Just like quantum mechanics is counterintuitive at science are very small. This is macro objects, but these things are really difficult to understand itself. Many of these things are spinning very rapidly, right?
Yeah. So what a neutron star is it's a whole star that has the same density as an atomic nucleus, right? So in the matter that you're used to, in the sun, and you and me, we're all made up of atoms,
Yeah.
right? And the characteristic of an atom is that all the mass is in the nucleus,
Yeah.
and all of the but all of the space is in the electron cloud, right?
Right.
And so that's what limits how dense normal atomic matter can be. And a neutron star is a star that is so heavy, the gravity is so strong that it pulled those atoms together.
Mm.
And what happens is that you have the electrons capture on the protons to make neutrons. Okay, and so you get rid of all the electrons
Yeah.
and all the protons. And then suddenly you have no electron cloud anymore. And therefore, then the matter doesn't take up any space, right? It has the same, so it's the whole thing is the same density as an atomic nucleus, which is much denser than normal atomic matter because all the space is taken up by that electron cloud.
Yeah.
And so that's what a neutron star is. And then there are many classes of neutron stars. They typically are spinning very rapidly. A slow neutron star does a revolution maybe once every few
Mm.
seconds, and a very fast one will do a revolution at once every few
Mm.
milliseconds. And these are these spinning ones that are spinning very fast are called pulsars. It's just a type of neutron star. There's other types of neutron stars that we'll talk about a little bit later, hopefully, called
Yeah.
magnetars. These are neutron stars with very strong magnetic fields. There's a whole zoo of neutron stars that have different characteristics, but they're all fundamentally this kind of the same thing, which is a whole star that has the density of an atomic nucleus.
Right. Yeah. So very dense, but not dense enough to become a black hole, right?
That's right. They're typically very borderline, though.
Yeah.
If you if they became even just 20% for some neutron stars, 50% denser, or then they would become a black hole. So these neutron stars. There's thought to be some maximum mass the neutron star can have, something like 2 solar masses, before it can't. Before it's just too big to even be a neutron star. It has to become even more dense, and thus become a black hole.
Yeah. And the electrons and protons are gone. So they don't have a charge.
They do not have a charge. Actually, we do think that neutron stars have protons and electrons in their crust.
Mm.
So the most of it, the structure is not that much like the Earth, but not unlike the Earth either, right? It has sort of this hard crust that's made up of that has like a crystalline lattice of
Mm.
protons, kind of like in a metal, and so there's some protons there, and that typically makes a very rigid crust that can deform and crack and have star quakes and stuff.
Wow.
But those are but the bulk of it is kind of like our mantle for the Earth, which is just pure neutrons, and is much softer and more fluid-like.
And they are, as you mentioned, spinning very rapidly. Some of them has a frequency of a few milliseconds. Does that mean that we are talking about objects that is hundreds of kilometers in diameter, spinning at a few milliseconds frequency? So does it mean that the surface velocity that we would observe on an object like this is a measurable fraction of speed of light?
Yeah, so actually neutron stars are typically only 10 kilometers across. But yes, it definitely is an appreciable fraction of the speed of light. I don't know the exact numbers, but it's in the percent to 10% the speed of light, the surface velocity. So that, yes, very, 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 very rapidly spinning for those very fast ones.
Yeah, and the demographics of this, Kiyoshi. So most of them we just observed once, right? They're not repeating, and very few are repeating.
Yeah, so for these fast radio bursts, the vast majority of fast radio bursts are what are called are what we've been dubbing one-off events, right? It just means that we've never seen more than one burst coming from that place in the sky before.
Yeah.
Now there was this breakthrough in 2017, before Chime turned on, where a team, I wasn't involved in the study, but a team, including some of my collaborators, found a burst that was repeating. They saw multiple bursts coming from the same place in the sky, and that was a big deal, because before that we thought that fast radio bursts could be caused by cataclysmic events, right?
Yeah.
Let's say the merger of two neutron stars or something hitting a neutron star that would destroy the star in the process. We thought you needed that much energy in order to do it.
Right.
In order to make these fast radio bursts. But once we observed these repeating fast radio bursts, that could no longer be the case. We had to produce that burst, but then the source had to survive to make another burst, hours or days, or in some cases, just a few seconds later. And that was the only known specimen of repeating fast radio bursts. So before Chime turned on, there had been 50 fast radio bursts observed, and one source that was repeating, and we'd seen dozens and dozens of bursts from that one repeating source. So that brings me to this other paper that we were going to talk about, which is the second source of a repeating fast radio burst. So as soon as Chime turned on, basically in the first 2 months, we observed 13 fast radio bursts compared to the 50 or so that had been observed before that.
Yeah.
And we saw those in just 2 months, but then we also saw a second example of a fast radio burst source that emitted repeat bursts. And actually, since this second specimen was discovered, we've published 18 more sources that we've seen to repeat.
And so the initial conjecture was it is some sort of a cataclysmic event. The source gets destroyed. But now we are seeing more and more repeating ones. So are they produced by two different phenomena, or what's the current hypothesis?
Well, that's the $1 million question. If you poll the scientists working in this field, and in fact, someone did poll the scientists working in this field, just say, gut feeling, are repeating FRBs the same phenomena as non-repeating FRBs? They were basically split down the middle. We have no idea. There are some people will just say, oh, the ones we haven't seen to repeat, those ones are, we just haven't looked at them long enough. If you look at them long enough, they will eventually repeat. And then other people will say, well, actually, not only these non-repeaters and these repeaters, not only are they different in the fact that they repeat and don't repeat, but there's also some morphological differences, some phenomenological differences in what the bursts look like that make us think like they might be completely separate phenomena. And no one really knows at this point.
Right.
to be honest.
Yeah, and so there's a lot to be learned. So you are involved in this instrument, Canadian Hydrogen Intensity Mapping Equipment, or CHIME. It is in Canada. Where exactly is it?
It's in Penticton, which is in the interior of BC. It's about a few hours drive from Vancouver, where I was for my postdoc.
Okay. Yeah, so near Vancouver. So this is a sort of a very different type of instrument, right? But so was the original goal of this instrument is to look for FRB, or they just sort of stumbled into it?
Well, the original goal was actually to do something completely different. So the name of the experiment has hydrogen intensity mapping in it. Hydrogen intensity mapping is an observational technique where you for mapping the large scale structure of the universe, mapping where's all the stuff in the universe on very, very large scales, things like galaxy clusters, galaxy filaments, and voids and stuff like that. It was designed to be this very wide field telescope. So by the metric that its claim to fame is it is the telescope that has the highest mapping speed of any radio telescope in the world. So that just means it can observe more of the sky at higher sensitivity. That product of both sensitivity and of sky area, it is where it really excels. And then while CHIME was being constructed, this fast radio burst field started to take off, and some of my collaborators realized that CHIME was the perfect telescope to do this, to look for fast radio bursts. All we had to do was add another digital backend, another basically cluster of computers to search the data that was produced by CHIME for fast radio bursts. And so they wrote a proposal, and they sought out funding, and they were funded, and then undertook this effort to create this new back-end search engine. If you can't quite call it a camera, but it's an instrument that just looks at the data that CHIME produces, and searches for it, and that turned on about and was commissioned just shortly after the CHIME telescope itself was commissioned, and you really started to make these amazing discoveries about fast radio bursts.
Yeah, and it is really a data analysis problem, right? So I would imagine because of the very short duration of these things. Obviously, CHIME is collecting a lot of data. So to go back into this large amounts of data and perhaps use some machine learning type techniques to detect them, I would think, right?
Yeah. So So I mean, CHIME really it's a software telescope. We like to say. So the reason it's able to have a higher mapping speed than any other telescope is the way the optics work. So we do a lot less focusing of the light than a normal telescope. Our mirrors don't work the same way as other mirrors. They don't focus the light as much as you would otherwise. What we do is we collect light, radio light, digitize it, and we focus it in software, and that allows us to look in many different directions at the same time. So that's the first place where this digital aspect of CHIME comes into place. Just the way it sees the sky, it's able to see more sky at higher sensitivity because it focuses the light digitally. And then once you have these images of the sky that are coming in on every millisecond, then searching those images for these flashes is actually very computationally expensive. And we have a cluster of computers that includes 128 computers, each with 20 CPU, 20 core CPU that process this data, and it uses these very clever algorithms to look for these flashes. We do make use of machine learning, but not actually in that first stage. We think we know with how to search the data initially for these flashes without using machine learning. We think we understand how to do that sort of using more just clever algorithms, but not machine learning algorithms. The place where machine learning really comes in handy is to reject false candidates. So unfortunately, interference is a huge issue for our telescope. Anytime someone comes within, a mile of our telescope with a cell phone, we see that, right? And so it's and there are TV stations from all over BC that we see. We see reflections of airplanes. We see satellites. We see all kinds of different weird and wonderful human communication signals that have nothing to do with astronomy, that make our telescope, that look like flashes of light to us. And we use machine learning to figure out which of those are coming from space and which of those are coming from someone that forgot to turn off their cell phone before they entered the observatory.
Yeah, humans are noisy, and it's becoming more of a problem for astronomy. I saw a picture of CHIME. Obviously, I don't know anything about this, Kiyoshi. It looked like sort of a solar panel type structure. Nothing seems to move. Did I understand it?
That's right. So it's I mentioned the mirrors before. So what makes our mirrors different than other radio telescopes, where you've probably seen pictures of a radio telescope that have a dish, right? Which those dishes are in the radio waves. They're basically mirrors, right? They reflect the radio light, and the chime dishes, the chime mirrors, don't focus the light in two dimensions the way that a normal dish does. It focuses the light just in one dimension. So it looks like a cylinder or like a half pipe, actually. So it's only focuses the light east-west, and that's because in the north-south direction, we focus the light digitally, like I described before. But it also, the big thing is, it has no moving parts. So we always just look straight up, and we're always just staring straight up and focusing the light north-south. But then we don't get to choose what part of the sky we're observing. It's just whatever happens to be overhead at a given time. But we've built it in such a way that we see a large swath of the sky in the north-south direction. And then because the Earth spins, we actually survey the full sky every single day. And so that really, if the thing you're going after is mapping speed, the ability to map out as much of the sky as possible, this is a great way to build a telescope. If you have a particular source that you want to observe, this is a terrible way of building a telescope, because if you want to observe that source, a specific spot in the sky, you have to wait until the Earth spins so that it's overhead. And and you don't get to look at that source very long. It only stays in our field of view for maybe 10 minutes. But we, for these large all sky surveys, we don't care. We're not in the business of studying individual sources. We're in the business of mapping out the whole sky and seeing what the sky looks like, sort of in a synoptic, sense.
Yeah, so it seems to be sort of ideally suited for somewhat rare phenomena too, right? Like FRBs.
Yeah, that's right, and that's why people, when this FRB field started to take off, people saw what this telescope that was being built for a completely different purpose, what it could do, and said, wow, this is actually the perfect instrument for this science. Let's add some instrumentation to it so that it can search for FRBs and make it do something completely different.
I don't know the history, Kiyoshi. I would imagine in 2007, when we first observed these flashes, there was some thinking perhaps it was some communication coming from extraterrestrials. But we have basically eliminated that idea, right?
Yeah, I mean, I wouldn't say. I don't think that's always been just sort of a fringe idea, right? I mean, you see, anytime you see, there's lots of weird and wonderful things that happen in the universe, and any one of them you might speculate comes from ET, right? But there's no reason. there's no, astrophysics is interesting, in itself, is able to produce just a huge diversity of different um,
Yeah.
of different things, right? So, I mean, it would be just very, from day one, we knew it was just very difficult to imagine this being uh, uh, an alien-like signal, right? Like, why are they making these big radio flashes? Where'd they get the energy to make something that could be seen halfway across the universe? Also, as soon as you saw two or three of these things, you have to say, okay, why did an alien on one end of the universe make exactly the same signal as was made by an alien on the other end of the universe, when they could never have talked to each other, right? They are billions of light years away from each other. That, these two aliens have nothing to do with each other, right? How could they possibly? Why would they make the exact same signal, right? And so, immediately you say, okay, this is just not. This has nothing to do with. This is just weird and wonderful astrophysics, and nothing ET
Yeah, so,
like at
so
all.
the energy, since these are radio waves, the energy requirements, I would imagine, are substantially lower than, let's say, gamma ray or something like that, right?
That's true, right? The energetics of FRBs is not. It's less energy than a gamma ray burst, less energy than a
Yeah.
supernova, right? It's less energy than all these things. What it is, what it is extreme in is how fast that energy comes out and how small of a region it's coming
Yeah.
from, right? So it's, you know supernova come from, these very big stars, and even though they produce the energy very fast, it takes a long time to get that energy out, because there's a lot of processes that have to happen, right? You have to heat a bunch of gas, you have to have nuclear decay, there's many things that happen. So typically supernova, they lots of energy comes out, but it takes weeks and weeks to get all that energy, to leave the star, right? And so the thing that made fast radio bursts really, really interesting was not the energy budget, but how do you get that energy out in a millisecond, without doing serious damage to
Right, right.
the star itself.
Yeah, we'll take a quick break, Yoshi. When we come back, we'll talk more about the mechanics of this as well as the magnetars.
Great.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we are back. Kiyoshi, we were talking about FRB, fast radio bursts, sort of flashes we observe from way out there, much further out from the Milky Way galaxy. And they are flashes, they are very short duration flashes of radio waves. The latest thinking is that they are created by very dense objects, perhaps like something like neutron star. We talked a bit about CHIME, the instrument up in Canada that is ideally suited to find these things. And there is a recent paper from the CHIME FRB collaboration entitled "A Bright Millisecond Duration Radio Burst from a Galactic Magnetar." Magnetars, in this paper, you say, are highly magnetized young neutron stars that occasionally produce enormous bursts of flares of X-rays and gamma rays. And of the approximately 30 magnetars currently known in our galaxy, we have seen a few exhibit the radio pulsations we were talking about as well. So before we get to the details of our own galaxy here, Kiyoshi, so the magnetars, could you put that in the context? You said this is young neutron stars. So is there some sort of a size differential here?
No, they're the same size as other neutron stars. The thing that makes magnetars its own class of neutron stars, or how we classify them is any neutron star where the majority of the energy that it's emitting is the reservoir of that energy is in the magnetic fields. Right, so that's distinct from, say, a pulsar. A pulsar is a neutron star where where it's stored energy is like a flywheel energy. It's stored in the spin of the neutron star. Whereas here, the energy is stored in the magnetic field. And any light that gives off, whether it be radio light or X-rays or anything, that light is energy that's been converted from magnetic fields into into radiation. So these magnetars typically have magnetic fields that are many orders of magnitude, millions and millions of times stronger than we can produce here on Earth. Magnetic fields are so strong that it can tear apart atoms.
Yeah, and so what makes the magnetars? So without knowing a lot about it, it would require sort of an arrangement on the object, right, for them to be magnetic.
Well, actually, I think magnetic fields are kind of ubiquitous in astronomy. Right, so we see magnetic fields all over the galaxies. We see them in stars. Our Earth has a magnetic field. Our Sun has a magnetic field. Right, all magnetic fields are just all over the place. And what I mean, magnetars, I think, are just a concentration of those normal magnetic fields. Right, so if you take all neutron stars come from the death of a normal star.
Yeah.
Right. So what typically happens is that a star runs out of fuel, it collapses and gets very, very dense and gets compressed from being millions of kilometers across to being just 10 kilometers across. And in certain circumstances, when that collapse happens, what will happen? What you get is a concentration of the magnetic field. So you'll have the normal magnetic field that the star had just naturally, the way all stars have magnetic fields, but then when it collapses, it carries that magnetic field in and concentrates it into this very you concentrate the mass, but you also concentrate the magnetic energy, and that causes that concentration really increases the magnetic field strength, because you have sort of the same amount of magnetic energy being compressed into a much smaller volume.
Yeah, I was wondering, so at the core of the magnetar, would there be anything different compared to a sort of a non-magnetized neutron star, or it's not required?
I don't know, and I don't know that we have a really good handle on the complete mechanics of magnetars. They do exhibit a lot of phenomena that are unique to magnetars, right? So one thing that was the way magnetars were first identified as their own class of sources was that they produce what look like gamma ray bursts. So normally gamma ray bursts are come from other galaxies and are very, very bright. But at some in the 90s, there were a certain type of gamma ray burst that was observed that didn't look like other gamma ray bursts.
Yeah.
The gamma rays that came off weren't quite as high energy as typical gamma ray bursts, and these were identified as coming from magnetars. And actually what they're coming from is seismic activity, star quakes on these magnetars. What happens is anytime you have seismic activity on all neutron stars can have seismic activity, but anytime you have seismic activity on a magnetar, that breaks or it reconfigures the magnetic fields. And since there's so much energy stored in those magnetic fields, that reconfiguration is a very violent, messy process, and causes a huge burst of X-rays and gamma rays that are associated with its own special type of gamma ray burst.
Yeah. So what do we know of the sort of the mechanics of the creation of FRBs? Is it sort of a similar process?
No, we have no idea. There are dozens of models out there that try to explain this phenomenon. So magnetars have long been, so we said that most people think FRBs come from neutron stars, and then most of the people that think that they come from neutron stars think that the neutron stars are coming from our magnetars, just because they exhibit such a wide and colorful array of phenomena. But exactly how that works, there are many competing theories. There's things that have to do with the reconfiguration of magnetic fields, things that have to do with seismic activity, the same way that the gamma rays are bursts. There are other models that think that postulate that this is actually coming from gas around the magnetars. The magnetar itself doesn't make a radio flare, but maybe it makes an X-ray or a gamma ray flare, and that hits gas that's around it and sort of creates a shock wave that then creates a radio flash. But these things, there's a large diversity of these models, right, and these explanations, and some evidence for and against each of them. But I think this field is still too young. We just don't have enough observations to really to be positive of which one of these is correct.
Yeah, that makes it exciting, Kiyoshi. Job security too.
Yeah, indeed. Yeah. Well, I mean, and then the thing that's really cemented, we still don't have a really good idea of what of how magnetars are causing these fast radio bursts, but we do now know that magnetars are causing fast radio bursts, and that's what this paper that we're talking about is about, right? So magnetars have always made radio pulses, but nothing like a fast radio burst. Remember, I said that these fast radio bursts, we see them in other galaxies. They're crazy bright. All right, we see them really far away. And magnetars, a normal radio pulse from a magnetar, you would never see that in another galaxy. It's just impossible. They're just too far away. But we saw this burst coming from a galactic magnetar, a nearby galactic magnetar that was bright enough that if we'd seen it in another galaxy, it would have been a fast radio burst. We could have seen it from a galaxy that was 10 million, 20 million light years away. And that's the first time we'd seen anything like that. So this was really bright for us. Our CHIME wasn't even looking in that direction at that time, but we still saw it just because it kind of came in through our peripheral vision. We only saw it to be maybe 1,000th as bright as we would have seen it had we been staring right at it. One other telescope also saw this burst, and that telescope was very it was a very small telescope. It was actually made up of just a couple K bands, and was still able to see this. That's just how bright this thing was, and that's because it was as energetic as a fast radio burst, but coming from our neighborhood, not coming from another galaxy.
Yeah, so you mean by galactic magnetar, you mean a magnetar within the Milky Way galaxy?
That's right. Yeah. So, and anytime an astronomer says galactic with a capital G, that always means our galaxy.
Oh, okay.
A little bit of subtlety of astronomer grammar there. And actually, all known magnetars are either in our galaxy or the Magellanic Clouds, very nearby galaxies. There aren't any, in far away galaxies, we just don't have the ability to see, for the most part, individual stars, but especially not things like magnetars, which tend to be harder to find.
Yeah, so going back to the mechanics, I know that we are still sort of exploring it. When we observe an FRB, do we also observe sort of accompanying X-ray and gamma ray flares?
There has never been an observation of an extragalactic FRB with any other type of flare. now this particular burst, this galactic magnetar, there happened to be X-ray telescopes looking at the magnetar at the same time, and indeed there were X-ray flares at the same time. So there were these little X-ray bursts that happened at the same time as this very, very bright radio burst. But those X-ray bursts, we never would have, if it had happened in another galaxy, we never would have seen it. Right. Whereas the radio emission, if it had happened in another galaxy, we would have seen it. So that's distinct. So there does seem to be accompanying emission at other wavelengths, other parts of the EM spectrum, but nothing that we would be able to see for this source, at least in other galaxies. And that's reinforced by the fact that we've never seen simultaneous radio and X-ray or optical or any type of emission from an extragalactic fast radio burst.
Yeah, so I wondered, since the galactic magnetar that we talked about had small X-ray and gamma ray flares, I wondered the FRB is created in some sort of a energy spectrum where you don't have huge amounts of energy released, but sort of moderate amounts of energy released. We won't be able to see the small flares of X-rays and gamma rays when we look out there, but ultimately we just see the FRBs.
Yeah, absolutely. And I think that's I think a lot of astronomers and astrophysicists have a very similar picture, and that's why there's actually many campaigns to try to characterize this multi-wavelength view of these of all FRBs and ones from magnetars, and that just takes a lot of coordination. You need to be looking at the same direction at the same time with lots of different types of telescopes, and you also and hopefully we'll see something like that. It also requires some luck, right? That you have to you have to get the right burst when you happen to be looking, right? And that's that's always hard. So we're looking for just that.
Yeah, I mean, it's exactly like a flash of a camera, right? You have to be looking, and it happens. In most cases, it doesn't repeat, and that makes it frustrating.
Yeah, indeed.
So, so this magnetar within Milky Way that we talked about. So, what is sort of the frequency? Do we know how many sort of magnetars might exist in the Milky Way galaxy, as an example?
Yeah, there's something. I mean, how many exist? I mean, we know of something like 30 of them that have been identified, but that's a tiny fraction of the total number of magnetars in the Milky Way. I don't know off the top of my head how many it is. It's certainly many thousands, if not hundreds of thousands, probably not millions, in the Milky Way. And we just know about the ones that are in our neighborhood, right? Actually, we do know of one that's a little bit further away towards the galactic center, but we don't. We're highly biased to see the ones that are nearby. We don't. It's hard. The ones that are far away in the galaxy are just harder to see.
So they're reasonably frequent, hundreds of thousands. We know that a magnetar could produce FRB. We have observed that. But could we say that not so all magnetars doesn't necessarily have to produce FRBs, right? This is sort of a special thing.
Yeah, but actually these broad statements are a little bit hard to make because we don't have a really good handle on the population of magnetars, I don't think, and we also certainly don't have a perfectly good handle on the population of FRBs and how frequent they are really over the whole sky in the universe. But I think the estimates that we have, which are rough, admittedly rough, but I think good enough to make statements like this, is that it's actually hard. Pretty common. There's a lot of them over the full sky, and the thing that prevents us from seeing, hundreds or thousands a day is just the fact that we can't look at the whole sky at once. And so it's actually hard. We don't actually think that there are enough magnetars in the universe to make, even if all of them behave the same way as this magnetar we saw in the Milky Way, it would still be really hard for us to make all the FRBs that we see in the universe. So there must be there must be some exotic type of magnetar or some phase that magnetars go into where they cause these bursts that we don't see that we're not seeing. The ones we see, the behavior we've seen in the Milky Way isn't enough to explain all the FRBs that we observe over the sky. So you need to add a little bit something else, and I think with a sample of one known and well-studied source, it's just hard to figure out what you need to do to get all the FRBs we see.
Yeah, I know that it is speculation, but do you think, what's your instinct? Do you think some sort of companion is needed for this to happen?
Yeah, is the companion needed for it to happen? I don't think it's needed for it to happen. There's evidence in some of the observations that there is a companion of many FRB sources. For instance, we've seen one repeating source that has a periodicity in its activity, right? So you typically see bursts from it coming. If you see one burst from it, you're likely to see a few more bursts and in the days surrounding that, in maybe a 4-day window, and then it goes silent for something like 12 days and then turns back on for another 4 days. So it has a 16-day period where it's on for a couple days, off for 12, and on for a couple more days. And that periodicity to its activity, we think requires some sort of companion, right? It maybe has something, maybe that periodicity has something to do with an orbit or precession, which usually requires a companion, or maybe, or at the very least, maybe some material that's orbiting it. It doesn't have to be a star. It could be just gas or something. We don't really know, but there's evidence, circumstantial evidence like that points to companions in some of the repeating sources. But yeah, I think it's just too early to tell, really.
Yeah, it could also be, for instance, if there is a black hole in the neighborhood and the source is rotating around the black hole, then you have periods of no information and then periods of information, right?
Yeah, absolutely. And if you want to throw something else into the mix it would be great if this had to do with black holes, because everyone, black holes are such interesting objects in themselves. To pair a neutron star and a black hole in a close orbit, that'd be a really interesting system. But if you throw compact objects like black holes or neutron stars into the mix, then gravitational lensing also comes into play. And that in itself is also super interesting. So I think there's just a very large diversity of scenarios that could solve that could explain these mysteries, and I don't think they've all been explored either theoretically or certainly not being well constrained observationally yet.
Yeah, it seems like a very exciting developing area. I know that you are intimately involved with CHIME FRB collaboration. So in conclusion, Kiyoshi, if you look forward 5 years, where do you think we would most likely make further discoveries and possibly get closer to explaining this in more concrete terms?
Yeah, so there's two things that I'm personally super excited for. So, a lot of what we know so far has been coming from individual discoveries, right? We discovered this one source that had periodic activity. We discovered, a handful of these repeaters. We had fast radio bursts coming from this galactic magnetar. These are all individual sources that we're learning about just by making case studies of them. But what we're not getting a good handle, or what we haven't done a good job of analyzing, is the population as a whole, right? What kind of, how are they distributed through the universe? What are the energetics of these from a population point of view? What are the environments of these of the sources? And CHIME, it discovers a lot of fast radio bursts. It really is a sort of a transition from going from dozens of fast radio bursts a year to hundreds of fast radio bursts a year being discovered, and we can start asking population questions now. And so that's one of the things I'm working really hard on. And no, population studies are always really, really hard, because you have these selection biases that you have to figure out, And so we're thinking very, very hard about, I can, of course, study the statistics, the fast radio bursts I did detect, but there's always, for every fast radio burst I did detect, there are many that I didn't detect, and I have to compensate for those biases.
Right. Yeah.
And so these population studies are really going to give us a much broader sense for what these FRBs are. What kind. Instead of just saying for this specimen and that specimen, what's happening for the population as a whole. So
right.
and that's coming up very soon, right? That'll be in the next a year or so. We'll have a much better handle on what the population is doing as a whole. The other thing that's really exciting on a 3 to 5 year time scale is what are called localization. So I said that these fast radio bursts are coming from faraway galaxies, and actually typically we don't know which galaxy a given fast radio burst is coming from, and that's because CHIME is really good at finding fast radio bursts. It's not so good at figuring out exactly what direction it's coming from. When we see a fast radio burst, there's normally an area on the sky about the size of the moon that we don't that could be coming from, and in that area on a typical spot of the sky, there's might be dozens or hundreds of galaxies. And when there's and that really limits, we can't ask questions about like what kind of galaxies do fast radio bursts come from, how far away are they, and that limits our information about the energetics, how energetic they are. And so we'd really like to have a better idea, for every fast radio burst, we'd like to pinpoint exactly where it's coming from. And we're actually building new telescopes right now that are going to help us with that. What we're going to do is we're going to build tiny copies of CHIME. They're about 1/8 the size, and we're going to put them in 3 different sites across North America, and they will be looking at the same place of sky as CHIME, and we'll use those to triangulate using a technique called very long baseline interferometry. We'll triangulate exactly where every burst is coming from. And VLBI, very long baseline interferometry, is a technique that is one of the most precise techniques in astronomy for figuring out exactly where a source comes from. It's the same technique that was used to image a black hole in that spectacular image that came out a couple of years back. And so we're hoping to use that technique to really nail down, for every one of these bursts, where is it coming from, and what galaxy, and what does its environment look like, and that should tell us a lot more about the population as a whole.
Yeah, so the localization, I would imagine it's important for us to also fully characterize if they're repeating, right? Especially if they're repeating in cycles of, long duration cycles. Localization is going to be important to really understand that.
Well, I think repeaters, we can pinpoint them well enough to know that if we see 2 bursts from the same place in the sky, we're pretty sure it's not a coincidence. It's just it really is 2 separate bursts. For 9 times out of 10, we're pretty confident when we see a repeater that really is the same source twice, as opposed to just two sources that are coincidentally very close to each other. But I mean, localization, what we'll do is it will tell us not just that it's the same source twice, but where is that source in its host galaxy, right? Where is it in is it in a nebula? Is it near the galactic center? Is there anything special about that area in the galaxy? And that's going to be just really illuminating.
Just one more quick question, Kiyoshi. This magnetar that we found in Milky Way, is it in any spatial position?
I don't think, as far as magnetars go. It's I don't know of anything. It's a very active magnetar. It tends to be very temperamental in the X-rays. It goes through these periods where it's just shooting off flares all the time. But I don't know of anything that's super special about its environment. It doesn't seem to be in a special place.
Yeah. Excellent. Yeah, this has been great, Kiyoshi. Thanks so much for spending time with me.
You're very welcome. Thank you. It's been great.
Thanks.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.